Um, I'm going to talk about lighting for older people and the people with visual impairment. Because of the Great East Japan earthquake about 2 years ago, followed by the nuclear power plant accidents, we had to restrict the use of energy, especially electric energy. And those pictures show what happened in Tokyo after the earthquake. Those pictures look very dark, but this is not because of the lack of exposure, but this is really what happened in Tokyo. The public lights were turned off because the lighting is very visible countermeasure to save energy, because people can see that people turn off the light easily. So we want to emphasize, we want to try to reduce the use of energy by turning off the public lightings. But public facilities became too dark for older people, especially some people with visual impairment. They couldn't go outside because of the very dangerous situation in some locations, if it's very dark. This picture is Ginza, Tokyo. The Ginza is supposed to be very bright, even in the midnight. But this picture was taken by Dr. Yoshiki Nakamura. He gave me this picture because this is very rare occasion. But on the contrarily, in Osaka, this happens in Osaka, they still have bright signboards. This is a kind of maybe some sightseeing location, Guriko's signboards. Neon sign was still turned on. Are they less sensitive to this kind of responsibility of energy savings? I should say no, because the distance from the epicenter of earthquake is farther than Tokyo, so that's why they still use some light for entertaining. But you can see several lights were off, even in Osaka. So we thought probably we have to make sort of recommendations, especially the light. Some location we shouldn't turn off the light because of the safety. We may have to make guidelines. So that's why we were focusing on lighting environment for people with visual impairment. In addition, this picture shows aging population in Japan. As you may know, already a quarter of people are over 65 years old. Japan is probably the most extreme case, but the Korea and also other countries will soon follow a similar situation. This picture shows the working population in Japan, over 60 years old. Vertical axis represents the year from 1990 to 2010. The vertical axis is a percentage of people who work. As you can see, the number of people working population is kind of reducing, even they have to work. Probably the environment is not good enough for older people's working conditions. So that's why we thought we have to develop good guidelines of lighting for older people and the people with visual impairment. About 5 years ago, actually, we established TC344, that is lighting for older people and the people with visual impairment. So currently I'm working for this committee as a chair, and the goal of this committee is to provide summary recommendations for the lighting provisions for older people and the people with visual impairment, especially in buildings. Dr. Peter Boyce was probably one of the earlier presentator of this symposium. He said, the most important problem is one of implementation rather than investigations. There have been already a lot of fundamental studies on older vision as well as people with visual impairment. So what we have to do is implementation of fundamental findings to practical conditions. There are already several existing publications, including CIE's publications. The CIE 123 is for low vision, lighting needs for the partially sighted. This publication includes a lot of fundamental studies review as well as practical recommendations, including some visual aids for low vision. This is a very useful publication. And also the second one, ANSI IES, that is American Society of Illumination. RP, Recommended Practice 2807 was published. This is also a very good publication. And this includes fundamental studies review as well as practice. But in our technical committee, we want to more focus on implementation part from fundamental studies to practical, the real world. The first line shows many reviews. Already many reviews are available about changes in vision with age. As you may know already, with age, our eye will reduce accommodation because already I have a problem. I need bifocal lenses, but I don't wear bifocal lenses because I feel dizzy when I wear. But we need some adjustment of accommodation with age. And also we're gonna reduce retinal illuminance because of the reduction of transmittance of the lenses, crystalline lenses. And also we have reduced luminance contrast of targets, especially visual target. And also reduced color saturation because of the reduction of transmittance of lens, especially in the range of short wavelength radiation. But we're gonna increase light scattered in the eyes because of the increased protein particles inside of lenses and eyeballs. And also we're gonna increase possibility of suffering from eye diseases, including cataract, macular degeneration, diabetic retinopathy, glaucoma, and optic neuropathy. Because of the reduction of retinal illuminance, we will need more light. But because of the increased light scattered inside of the eyeballs, we need less luminance of light sources to reduce glare. So the question is, questions are how much more illuminance is needed for visual tasks for older people? And the second question is how much lower luminance is needed to ease glare? The third one is how much more short wavelength radiation do older people need to stimulate their bioclocks? The third one is already Professor Kobayashi mentioned. So I'm not going to speak the detail of this part. So I'm going to focus on the first two questions in my presentation. On the first question, how much more illuminance do older people need than young people? There are several visual performance models available already. One of them is RVP model, Relative Visual Performance Model, developed by Dr. Mark Ray in 1991. RVP model is sort of model to estimate visual performance, relative visual performance in terms of percentage by using some variables, including task luminance, contrast, and illuminance, as well as age. According to the RVP model, a 65-year-old person needs a few times higher illuminance than a 20-year-old person for the same visual performance, but for the very normal letter size conditions. For comparison between young and older people, you can see this picture. The vertical axis represents illuminance. Horizontal axis represents illuminance. Vertical axis represents relative visual performance. So you can see some difference between two age groups. But for max illuminance level, you cannot reach the same performance if you are over 70 years old. But very close, like you can get still 90% of visual performance with corrected lenses. There are several ways to estimate how much light needed for older people. Some study was done. This study was done by Okajima and Iwata. They analyzed retinal illuminance based on the two-factor model. Two-factor model was developed by Pocconi. This picture shows a two-factor model. Horizontal axis is wavelength. Vertical axis represents transmittance. So as you can see, and also you can see the legend in terms of age, starting with 22 years old to 80 years old. As you can see, with age, you can see reduced transmittance, especially for the short wavelength conditions. This is especially for short wavelengths range, you can see large variation, difference between younger and older subject. So according to this study, older people need 1.3 times higher illuminance than the young people for the same retinal illuminance. How about the preference of illuminance level? This study also asked older and young subjects about their preference of illuminance levels. The study said about 1.5 to 2.0 times higher illuminance they need compared to younger subjects. But as you can see, a large variation exists in the multipliers to illuminance for older people. You can see 1.5 or 1.3 or maybe a few times higher. The IES RP28 has a good answer to this question. They chose the maximum level in the range of illuminance recommendations. For instance, they have some range for normal lighting condition and normal visual tasks. They do have like 300 to 700 lux for that kind of tasks. They said people have to choose the maximum level, which is 700, to achieve comfortable illuminance level for older people. We are probably follow these solutions. However, we should determine what is the minimum font sizes and the contrast for these illuminance levels, still, so that still older people can see the target, and also older people can get 90% of relative visual performance. But we need a consensus from international consensus to get recommendations for illuminance levels. On the second question, that is how much lower luminance is needed to ease discomfort or disability glare. There are two types of glare, disability glare and discomfort glare. Regarding disability glare, already equation was already established. This is a nice, very decent equation composed of illuminance at the eye caused by the glare sources, and also angle between the light source and the line of sight. As I said, this is a well-designed equation. We can utilize this equation for practical implementations. But I'm gonna back to this implementations later. Compared to disability glare, I'm gonna skip. Compared to disability glare, discomfort glare is not well defined yet. And also the comparison between older people and younger people were not agreed yet. For instance, this picture shows the result of Bennett study in 1977. The vertical axis represents BCD, which is a borderline between comfort and discomfort. That is a threshold between discomfort and sort of okay luminance levels. Horizontal axis is age. As you can see, with age, older people tend to choose lower BCD, which means older people are more sensitive to glare than younger people. After this evaluation, people already have believed that older people are more sensitive to glare than younger people in terms of discomfort glare. But a recent study didn't show that the same conclusion. Some of the study showed opposite direct orientations. Some of the studies said young people are more sensitive to glare than the elderly. This study also says so. This picture shows Nakano's study, which is a very recent study. Horizontal axis is luminance of light source. The light source was very large, like an office light source, like 30 centimeter by 120 centimeter size. And by changing the luminance of the light source, they subject evaluated degree of discomfort by using 7 scales, probably. As you can see, if you compare older people's sensitivity than younger people, this said that older people had more glare to the same luminance level. So which means older people are more sensitive to glare. So we didn't know the answer. I did some study to confirm which is correct. This picture shows a setup of experiment which I used. The subject was sitting in front of the light source. This is just a partition. A partition had several holes. The subject looked at the light source. Subject looked at the fixation, central fixation point. While looking at the fixation point, peripherally, experimenter presented a glare source. And they did the BCD evaluation, which is borderline between comfort and discomfort. We used different colors for light sources, blue, green, yellow, and red. As you can see, different peak wavelength conditions. So as a consequence, this is actually experimental results that we had. Younger subject, older subject, and horizontally eccentricity angle, because we changed the locations of the discomfort glare source. The vertical axis is BC luminance, the threshold luminance. In terms of color, you can see light sources with more short wavelength radiation. People are more sensitive to this kind of light source compared to light sources with more long wavelength radiation. So both are consistent between two groups. But if you compare the sensitivity in glare between young and older subjects, you can see the threshold luminances are larger, higher for older people compared to younger people, which means older people were less sensitive to glare. So this is still ongoing. We do need more results which compare different age groups to get the answer. But it is very important to find or define mechanisms of discomfort glare to identify which is correct. One of the study said older subject chose higher BCD luminances than young people for short wavelength LEDs because, as you can remember, the transmittance for older people in short wavelength range is less than young people, especially over 80 years old. But they selected similar BCD for long wavelengths like red LEDs, which is very consistent to our study as well. And several already studies have been done for identifying visual models of discomfort glare sensation. Some studies said among visual sensitivity functions, S-cone function is more important for discomfort glare sensation. Our study did a similar experiment, and we found the same tendency. In addition to that, we also found that rods also important. The contribution of rods to glare is very important. So we need an appropriate model. We have to compare those models to find the most decent one. And also, what we know is regardless which model we use, it's confirmed that lamps with short wavelengths look more glaring. So we may need some consideration when we select light sources. This is my model, but we don't have enough time to look at these details of this equation. I'm gonna skip, but the most decent solutions for lighting for older people is probably very antithetic. This is very antithetic relationship between. We need very high illuminance for visual tasks, but we have to reduce glare by reducing luminance of light sources. They are contradicting each other. But as you can consider, probably the task ambient lighting system may be one of the good solutions, because we can reduce some scattered light from surrounding area by reducing ambient illuminance level. We do need task illuminance, higher task illuminance, so we do need some controlling system for especially task lighting. I compared many task lighting conditions, and we found we need a very wide distribution for especially older people to read the newspaper or books. Regarding the ambient lighting system, we kind of developed wooden ambient lighting with LED systems. We use some leakage of light for downwards, but this is mainly for upward lighting. This is sort of indirect lighting. We thought that we have to eliminate any visible light sources from older people's vision to reduce glare, but we do need a higher illuminance level to make a safe environment. By using ambient light and the task lighting system, we asked older people and younger people to compare their preferred illuminance levels. We asked them to choose 3 illuminance levels. One of them was the maximum acceptable range of illuminance, and also the minimum acceptable range, and the most preferable illuminance levels. In terms of ambient illuminance, we changed ambient illuminance levels. The vertical axis represents ambient plus task light. This is a summation of illuminance between ambient and the task illuminance. If you compare older subject and the young subject, you can see a little bit different results, but the tendencies are very similar. But what you can see is for older people, you need lower maximum luminance, because probably to reduce glare, but they need higher illuminance levels because they do need higher task illuminance level, and a little bit higher preferable illuminance levels for older people. So what we learned is we need careful selections of lighting conditions for older people, and we need the availability of controlling systems so that they can choose by themselves, especially for task lighting systems. And what we found was also people may not know what appropriate lighting conditions are, especially this tendency is stronger for older people. So we do need implementation. How about the time? It's already 6 o'clock. Still, can I? 10 minutes or something? 5 minutes?
No.
Oh, no, let's go.
No problem.
Okay, let me have some 10 minutes. maybe. Okay, so we do need some lighting design tool, which is a visual model, which is more practical than conventional fundamental visual models. So in order to implement research findings, we try to develop some of the tools. One of them is based on varying luminance equation, which I showed earlier. Some sort of image processing system, computerized image processing system is already available, so we can utilize that kind of system to demonstrate how to use the varying luminance filter to visual task. I did calculation based on what we already know, and I apply that calculation to image processing system. So this is what you can take. I took this picture, and this is actually for young subject. I apply young subject filter to image processing system. Compared to young subject, you can see some larger. This is actually older subject, and maybe you can see this is probably better to understand what's the difference between two age groups. The size of the varying luminance, size of the veil is larger for older subject compared to younger subject. This is actually based on the equation which I showed. And also, if you look at the picture on the book, you can see the lower contrast for older people's simulation. So this might be useful for younger lighting designers to understand what happens in what older people can see. Portfolios are also a good demonstration tool. Portfolio comparing before and after refurbishment might be very helpful to understand what we should do. But this may not be a good example. This is a picture of, which I took in Kyoto Station near a shop. You can see the entrance of the shop here. Probably there are many folds on the edge of the gap. Actually, there is a probably 15 centimeter gap between the shop level and the corridor level. So because of some accident and some compliment from customers, they put a sort of stage with handrails. In addition to that, they put the very psychedelic orange marks and put some warning signs here. So this might be a decent solution after they got some compliment. But this is not probably what we are looking for. We do need, when we do lighting design or visual environmental design, we have to come up with better solutions for this kind, to avoid this kind of problems. We did some interview with people with low vision. For instance, the staircases are one of the very dangerous locations. This station, actually this is Kyoto Station as well, and the architect wanted to probably coordinate whatever we can see in a single color, but sometimes it's very difficult for people with low vision to see where is a step, a tread, and the step rises, a step noses. So from the top of the stairs, what we can see is this kind of picture. This is, you can see one step here and another step. But if you look at this picture, the picture looks as if there is only a single slope in front of you. Probably this is a better solution. This is actually Fukui Station, which our university is located. Where our university is located. They put the white stair nodes on the edge of the tread surface. So to increase the contrast of the nodes against the background, so you can see better. You can identify just each step. So this is a good solution. So similar things happen when I visited Louvre Museum in France. You can see this is one of the famous locations. But all the things are made of marble. So from the top of the stair, you can see just a slope. You can see, if you carefully look at the steps, you can see different steps. But this is one of the very dangerous locations. We need noses with different colors to increase contrast, luminous contrast. So this is another example of demonstration. We should avoid stripes perpendicular to a corridor. If you look at this picture, this is just a stripe, decorative stripe on the surface of the floor. There is no level. One of the recent study did the experiment to ask subjects with low vision to just walk around. What they found was that most of the subjects confirmed if there is a gap between this level and this level by using their canes, by using their feet. So this might be a very dangerous condition, so we have to avoid some stripes vertical to a corridor. So we have many that kind of examples, but this is a tactile tiles in station concourse, but I probably may have to skip because of the limited time. So the purpose of illumination is to increase illuminance level on surface of the task, but also we have to consider how to use illumination. We do need, when we ask people with low vision, they did say to perceive the depth of the space, they do have to have sort of a single line along a corridor so that they can understand the corridor, which way they have to follow. So also this kind of carpet, this is actually carpet, by changing the materials. So you can see different touch of the surface of the floor. So people can understand this is the end of the corridor. Of course, we have to increase the size of the signs as well as pictographs. This is a Japanese case, and compared to France, this is men's room compared to ladies' rooms in Japan. But in France, they do use orange for both genders. But we may need some consensus or some international consensus in the use of colors as well, maybe. So this is kind of detail, so I'm gonna skip this part. But so I made this presentation because I do need your help for the work of TC 344. We do need international consensus on illuminance requirements, especially for task ambient lighting systems. And also about practical lighting solutions, we have to establish visual models which can be applied to the real world. As I showed demonstrations, we wanna collect demonstration data of how to apply the visual models to practical lighting designs, especially for older people. And we have to make sure what we can recommend for health. This part, I didn't present this part, but some of my international co-workers are doing this part of the works. So we have to make sure what can we recommend for health of the elderly and the visually impaired. Okay, so thank you for your attention.